By Newton's laws, we're going to be looking at situations where not only is it going to be just like a one-dimensional force, there's going to be two dimensions. So we're going to have to bring in the trigonometry. Okay? So we're going to have situations where objects are at equilibrium, which means they are not accelerating. And we're going to have situations where the system is accelerating. So we have basically two scenarios. So you use Newton's laws with free body diagrams to determine forces, accelerations, and masses. Do you remember on the quiz today where it said constant velocity at the bottom of the quiz? So in that case, acceleration is, and therefore, because F net equals ma, and a is 0, then the net force is. So if the net force is 0, all the forces have to be equal and opposite. They have to be balanced. Okay? So these are problems where there's going to be no acceleration. Identify the forces, draw the free body, and then solve such that the sum of all the forces is 0 in the x and the sum of all the forces in the y is 0. Are you guys okay reading this? I'll put a note for you. The sum of all forces in x and y are balanced equal and opposite. Okay? That would be like if I was set up to like a torture device where like these ropes pulled my body parts left and right. Would I go anywhere? Say like 10 newtons left, 10 newtons right. They're balanced, right? And then there was like maybe something attached to my leg, my two legs. Like, what if I was 10 newtons left, 10 newtons right, but then 10 newtons on my legs down? Where would I go? I would accelerate down. So you would need an up force to balance the down force as well, right? Okay, so think about like this clock. Why isn't this clock falling towards us? It's attached to the wall somehow, right? Somehow there's some forces being balanced on that clock, right? What about this pig? How come this pig is not accelerating down towards me to hit me in the head? This thing has weight, does it not? If I severed the string, what would happen? It would fall. So that up force is matching this down force. Like this up force, it's totally determined by the weight of this. What if I put on something heavier? Could the string hold it? Maybe. Yeah, to a certain degree. What if I put on something heavier and then it held it? Would the tension in the rope be higher? Because it would have to match the weight. What if I put on something so heavy that the tension couldn't match it? What would happen? The tension would cause the rope to snap. Okay? So this tension force only has to be as strong as the weight. And the tension in the string can change according to the weight. Okay? So we're going to be doing some problems here that involve this idea. This one here, for example. I want you just to imagine this as like one of those like exit signs. You know, you're walking in a public building, you need a close exit, there's these exit signs, right? Well, this one is hanging from a couple ropes. This one's hanging from a couple ropes. So is this sign accelerating? It's at rest, right? So if it's at rest, any forces that are acting on it must be balanced. Let's identify these forces. Let's focus on the sign. A sign has mass and therefore has weight. What is its weight? It's the down force, right? So this force is Fg, this one right here. What is holding it up? The strings, right? So call this one tension 1 and call this one tension 2. I'm going to draw it off to the side. Here's Fg. Here's T2. And there's T1. Are you guys confident in that free body diagram? The tension exists in the string. Do you agree with that? So the tension vector is along the string. Fg always points down. Are there any other forces acting on this object? That's tension 1, I believe. You can see that the tension in the rope is the same. Do you see that? Okay. We're trying to find the weight of the object. So if it's not accelerating anywhere, how is this down force being balanced? How is that down force balanced? It must be balanced by the up forces of those strings. Do you agree? But those up forces are not perfectly vertical. They're at an angle. So what do you have to do when the force is at an angle? Very nice. You have to resolve it into its x and y components. So we can call this one T2x and this one T2y. Do the same thing over here. And remember, you draw them tail to tip to form the resultant vector. This one's T1x and this one's T1y. So could you come up with an equation for F net in the y component? Remember, F net is equal to the sum of all forces. So what forces are acting vertically? T1y plus T2y. Is there any other forces acting vertically? Fg. But here I have T1y and T2y written as positives, and their vectors point up. So I should write Fg with a negative. And now here comes the most important part. The system is not accelerating, so the acceleration is 0. So F net is 0. That's the most important part. T1y plus T2y minus Fg. Now, if you wanted to make a statement about this system that really summarized it very well, is if you threw Fg to the other side. Now, I really want you to just think about that equation right there in the box. The downward pull of the object, in other words, its weight, Fg, is completely balanced, equal and opposite, by the up components of the two tensions. So that equation in green, compared to the free body, the down arrow, Fg, is obviously this. So then T1 and T2y are these. These two blue arrows, if you added them, they would be the exact same length as this down arrow. Does that make sense? Okay, so let's switch gears. Let's go to F net x. What forces are acting in the x component? Yeah, just T1x and T2x, right? Those are the only forces that are acting. So, because I don't really know anything about their relative sizes, I think, I'm just going to put the T2x as a positive and the T1x as a negative because it's right and left. You guys okay with that one? T2x minus T1x. Just because they point to the right and one points to the left. And is the object accelerating? No. So what is F net? 0. So then what could you say about those two forces? They are the exact same magnitude. If you subtract them and get 0, if you subtract two things and get 0, they have to be the same, right? So those are the same magnitude, just opposite in direction. Okay, and now all we have to do is do some trigonometry, and then this question is solved. Okay, so we just did some basic geometry to get the angle at which the tension force is acting. I just use parallel lines to find the 45. Okay? So now what we can do is we can take that 45 degrees, put it here and here. Okay? Let's see if we can find some of these. We have to have a value. What's the tension in the rope? So the hypotenuse is 100 newtons for each rope, right? And that's the hypotenuse of these right angle triangles. So you have a hypotenuse and you have the angle. That means you can find both of those components, T1y or T1x. Either one is fine. Okay? So could you find T1y? Absolutely you can. What would you write? 100 sine 45, that equals T1y. It also equals T2y, do you agree? 100 sine 45. Make sure you're in degree mode. They're both 70.7 newtons. So yeah, the x are the same thing because 45 degree angle, 45, this is a 90, so these are isosceles. So yeah, the 70.7 everywhere. This one's 70.7, this one's 70.7, 70.7, and 70.7. So what is FG then? Twice 70.7. Do you agree with that statement? Do you agree that FG is twice 70.7? Yeah, because it's both of them. You have to add them up. So 141.4. Sig digs is 3? 3 sig digs? So 141. How do you guys feel about that? It looks like a lot, but if you keep it simple and go slow, you should have it. Oh, fine. Okay. This one wants us to determine the unknown forces. So this is a bit of a different setup. Yeah, if you really want to, yeah. This is a bit of a different setup. You have a mass at equilibrium. I guess I'll write it for you guys, what these are called. These are called hanging mass problems. And the key here is that they're at equilibrium. So therefore, F net is 0 in the x and the y components. So, like, how do you hang a mass? How do you hang up a picture in your house? Like, the picture has weight, so you have to balance the weight. These problems, though, are interesting because they don't just put the tension in, they don't put the strings vertical, they put the strings at angles, or in this case, the F2 string is actually horizontal. So that's interesting. So let's take a look at this, and let's draw a free body diagram. We'll have to draw a free body diagram maybe off to the side here. So there's the mass, big red dot. There's the mass. The mass obviously has weight, Fg. Now to support that weight, the mass has strings attached to it. One of the tensions, let's call that tension 1, is off at an angle like this. And the other tension is off at a horizontal like that. That's the free body diagram. Are there any other forces involved? It's not in motion, so there's no friction. It's not resting on a surface, so there's no normal force. It's got a string that's pulling on it, so that's tension. And it's got mass, so therefore it has gravitational force. Those are the only forces acting. So what is balancing this Fg? Fg points down. So where is the up force that balances this? What part of T1? Which component of T1? Yeah, this right here, that T1y, that's what balances the Fg. Okay, well, what balances the T2? Yeah, very nice. T1x. So because these are at equilibrium, they have to be balanced. So then T2 equals T1x. What is happening? And what's the other one in the y? Fg equals T1y. So we have to use what's given to us. And I'll just write a little note here. y component, x component, if it's not already obvious, just trying to stay organized. We have to use what's given to us. What's the only force that's given to us? 50. Now that's probably, in your everyday experience, that's probably the weight that the force value that you would know, because you could weigh the object. So this example, I would say, has real life possibility. So Fg is 50. What's the formula for T1y? Well, now we need to zoom into this picture. I have to use trigonometry. Okay? So if I was to break this into its components, this angle would be 60. We called this one T1, right? We're not calling it F3, calling it T1. Okay, so what's the formula to get this this opposite side? Sine 60 is op over hype. Do you agree? The op is T1y and the hype is T1. Sine 60 is op over hype. Okay, I'm going to do it again over here on this free body. This one's 60. What formula relates sine of 60? That would be op over hype. T1y over T1. Solving for T1y, it's T1 sine 60. Okay, there's T1y. Okay, so T1y, we can now sub this in. T1y over here. T1 sine 60. And now you can solve for T1. How would you solve for T1? Just divide out sine 60 on both sides. So 50 divided by sine 60. How many sig digs we rocking? 2? So 58. And tension is a force, so tension has direction, but tension is always along the rope, or the string, or the cable, whatever it is. So the tension force is along the string and opposite to the opposing force. Okay, now how are we going to get T2? You got to look at this slide, right? It's balanced by T1x. Okay, T2 and T1x are balanced. You can see here, T2 points to the left, T1x points to the right. So just like we got T1y using sine, how could we get T1x? Yeah, use cos. So cos of 60 equals T1x over T1. So T1 cos 60 is T1x. You could, yeah, you could, yeah. But I'm just going to use T1 because I have T1 already. Okay, so T1 cos 60 is the value for T1x. So I can solve for T2 now. times T1 cos 60. So it's at 57.7 times cos 60. .8, so 29 newtons along the rope. So these ones are challenging, for sure they are. But they're definitely not beyond your skill set. Using geometry and SOHCAHTOA to relate forces that are balanced. Okay, so just two questions for your homework tonight, 15 and 16.